Hello, everybody. I hope you're doing well. Today, we are going to correct exercise 4 from the first worksheet. So we are going to consider the function f of z, which is equal to e to the 2z times e to the 1 over z. We want to show it admits a Lorentz series expansion on the annulus center at 0 and with radius, smaller radius 0 and bigger radius infinity. So this is the 0, and then we want to find Lorentz expansion in the region outside. We want to show this exists, and actually, in general, it's a bit difficult to compute. We want to start by computing the coefficient a minus 1, so the coefficient corresponding to z to the minus 1. And then from this, we will also going to have an idea how to find the formula for a minus 2. So first of all, let's consider the function fz equal to the e to the 2z times e to the 1 over z. So this function is holomorphic almost at every point. We have a problem only when z is equal to 0. So this is holomorphic on c minus 0. And this is another way to say the annulus center 0, inner radius 0, and outer radius infinity. So we have a function which is holomorphic on this annulus. And then by the theorem seen in class, this function admits a Lorentz expansion. So how are we going to find the Lorentz expansion for f? The idea is that we are going to use the power series expansion for the exponential. So let's find the coefficients an of the Lorentz expansion. We use that e to the z is equal to the sum from 0 to infinity of z to the n divided by n factorial. We are going to use this formula, but before that we are going to use a small trick, and namely we remember that e to the a times e to the b, this is equal to the e to the a plus b for all a and b complex number. So this implies that my function f of z is also the exponential of 2z plus 1 over z. So now let's apply the formula for the exponential to this expression. So this implies that f of z is equal to the sum for n going from 0 to infinity of 2z plus 1 over z to the n divided by n factorial. So before going on, we want to compute this power here, to z plus 1 over z to the n. So this is easy to do using the binomial coefficients. So what is 2z plus 1 over z to the n? This is the sum for k going from 0 to n of the binomial coefficient n over k times 2z to the k times 1 over z to the n minus k. So let me simplify a bit this expression. So the binomial coefficient, remember it's n factorial divided by k factorial times n minus k factorial. Then here we have 2 to the k, and here we have z to the k times z to the k minus n. And we can put this all together, and it comes to z to the 2k minus n. So let me write it already. 2k minus. Okay, so we have this formula, we can substitute it back. And we find some from 0 to infinity of 1 over n factorial, then k going from 0 to n, and then n factorial, k factorial times n minus k factorial 2 to the k times z to 2k minus n. Okay, so we see here 1 factorial goes away, and we find this formula. To the k divided by k factorial n minus k factorial times z to the 2k minus n. So this is, we see it's a Laurent expansion for f. The only problem is that the exponent that we have of this z depends both on k and n. So in principle, if I ask you what is the coefficient of z to the 4, for example, we have to consider several values of k and n. So all values of k and n such that 2k minus n is equal to 4. In our case, we have to consider the coefficient of z to the minus 1. So we want to find a minus 1. Also, we know that this series can be written as a Laurent series. Let's use an m here. Z to the m. Sorry, this goes from minus infinity plus infinity. And so now we want to find a minus 1. So the question is, when is 2k minus n equal to minus 1? So, and here we see that this happens if and only if n is equal to 2k plus 1. So in particular, n must be an odd number. And then for every k going from 0 to infinity, we will find exactly one n having this property. So for every k running from 0 to plus infinity, there is exactly one n satisfying this relation over there. Let's call it star. This relation. So this means that what is the coefficient a minus 1? So this means that a minus 1 is equal to the sum for k going from 0 to plus infinity of all these coefficients over there, where n and k satisfy the relation star. Okay, so then I can write here 2 to the k factorial, n minus k factorial. But now we have to remember that n satisfies the relation star, so I can substitute here instead of n, I can put 2k plus 1. And so we arrive at the formula that we wanted. K factorial, and then here we get 2k plus 1 minus k, this is k plus 1. So this is the formula that we wanted. So this finishes the first part of the exercise. The second part asks for a similar formula for a minus 2, if I'm not mistaken. So, right, so we see we found this formula for a minus 1, and now we want to find a minus 2. And the procedure is really similar. So we just have to impose a new condition. So we want to find a minus 2. So also here question, when is 2k minus n equal to minus 2? This implies that n is equal to 2k plus 2. And as before, so this implies that a minus 2 is the sum for k going from 0 to plus infinity of 2 to the k factorial, n minus k factorial, but this time we know that n is equal to 2k plus 2. So in the end, we find a slightly different formula, 2 to the k divided by k factorial. And here we have 2k plus 2 minus k, which is equal to k plus 2 factorial. And this is the formula for a minus 2. So we can here compare the two formulas. So here we have k plus 2, and here we have k plus 1. And I see that here we have a pattern. So a minus 3 will be the same with the k plus 3 and so on. Okay, thank you for watching.